video, we're going to be taking a look at the first law of thermodynamics. We're going to cover all of the concepts, the sign conventions, and then take a look at a few example problems to see how it's applied. So the first law of thermodynamics is basically showing the conservation of energy in the lens of thermodynamics. We have delta U, which is the change in internal energy. We have Q, which is the heat. And we have W, which is the work. Now, depending on where you're getting your information from, the biggest cause of confusion is actually whether this is a plus or minus sign between the Q and the W. So if you search the internet, check out different YouTube videos, there's a lot of confusion around this. Now, if you're using a plus sign and summing up the heat and work, that means you're taking the perspective of the system. And we'll get a little bit more into the system and surroundings, but you see a little diagram I have here to the right, so you can see what the system is. And then if you are subtracting Q and W, then you are taking the perspective of the surroundings. So you're really talking about the same thing from two different viewpoints. And we'll talk about why you would do those things a little bit later. So taking the view of the system is very common for chemistry. It is also used in physics a bunch as well. And then the minus for the surroundings is a common viewpoint for physics, a lot more so in the engineering world. In this video, we're going to take it from the perspective of the system. That seems to be the most predominant perspective, and one that I think that is fairly logical as well from what we're looking at. So let's go ahead and dig a little bit deeper into this. So we have a system. My system is typically going to be some container filled with some gases. We have some molecules kind of bouncing around, applying some pressure inside of this container. And then we may have something like a piston that can possibly move up and down and do work on the surroundings. So the surroundings is basically just sort of the environment around the system. Now, Q is either the heat going in or out of the system. Now, if it is going into the system, we will call that positive because it's going to raise the temperature, which then in turn changes the kinetic energy, average kinetic energy of those molecules, and then that internal energy will rise as that temperature rises. If heat is being released, that is going to be negative. This one would be known as exothermic because the heat is being released, and then this would be considered endothermic because the heat is being absorbed by the system. Now, for the work values, now work is just basically a transfer of energy. If the system is doing work on the surroundings, that is going to be considered negative because the system itself is losing energy and transferring it to the surroundings and possibly pushing something like a piston downward and applying a force over a distance. Now, as those little particles have their random motion and they're bouncing around, they are collectively going to transfer some energy to, say, the bottom of this part of the system and then push it downwards and then transfer some energy to the surroundings. On the other hand, if we have the surroundings pushing and applying energy into the system, that's going to be considered positive because we have energy flowing from the surroundings into the system. And then, as I mentioned before, if you were taking more of the physics engineering type of perspective, then it's going to be minus W, which is considering that you're taking the view of the surroundings. So that would actually flip these signs and it would be negative over here and positive over here, because if you're taking the view of the surroundings, then that means the system is pumping out energy to you, which would be considered positive, or the surroundings are pumping energy into the system. Therefore, you would be losing energy by transferring it to the system. Okay, as I said before, in my experience, this is the most predominant convention. So we're going to go with that one and the plus sign between the Q and the W. So let's take a look at 3 different examples, and then we can see how the first law of thermodynamics is used in some various cases. For the first problem, we have 100 joules of work are done on a gas. Okay, so not by the gas. So if it was by the gas, then it's the system to the surroundings. If it's on a gas, then that means that the work is going to the system. Therefore, it should be positive. So I'm going to go ahead and just kind of diagram it out just to keep a physical note of the things that I'm reading. If the internal energy ends up decreasing by 70, so my internal energy decreases by 70 joules, then how much heat got transferred and was it in or out of the system? So we're looking for our Q value here. So a lot of the stuff mathematically is going to be very simple. So it's just really understanding some of those basic concepts of where the energy is going and whether it's positive or negative. So we have our delta U is going to be negative 70 joules because it has a decrease of internal energy, and that equals Q, which is our unknown. And then we said that the work value is done on a gas and not by the gas. So that means that we have 100 joules right over here. So just some simple algebra. We're going to go ahead and subtract 100 from both sides. And then that would leave us with a final Q value of negative 170 joules. The second part of the question says, and was it in or out of the system? That one is definitely out because of the negative sign. That means it's exothermic. The heat is leaving the system. Let's go ahead and take a look at our second one. We have 60 joules of work are done by the system. Okay, so that means that the gas is doing work. So then that means we have energy being transferred out into our surroundings. And I got 200 joules of heat transferred. So we have 200 joules of heat being transferred into the system through a heating element. What was the change in the system's internal energy? Did the temperature of the system increase or decrease? So we're going to go ahead and look for our delta U. We said that the heat, it is positive because it's getting transferred into the system, as mentioned by the problem right over here, 200 joules of heat transferred through a heating element. And then we also said that our work is a negative value, so we'll say plus negative 60 joules. So then 200 minus 60, we have 140 joules as our final answer and our change in internal energy. And it says, was the change in the what was the change in the system's internal energy? So check to that one. And did the temperature of the system increase or decrease? Well, the internal energy is going to be proportional to the temperature. So that means the temperature is definitely going to increase as the internal energy increases. And then obviously that would happen vice versa as well, as in if we have a negative delta U, then our temperature is going to drop. All right, so let's take a look at our last one. A gas initially has 200 joules of internal energy. So it has, we'll say, a U naught of 200 joules. This gas does 50 joules of work. So again, taking a look at a few keywords is going to be really important in picking up the sign and whether the energy is being is entering or leaving the system. So it does 50 joules of work. So the work is being done by the system to the surroundings as it gets 180 joules of heat transferred to it. What is the final internal energy? Okay, so we're taking our delta U and we just are breaking it open to final minus initial. So we got our initial internal energy and we're looking for our final, which is our UF. So UF minus 200 joules equals Q of 180. We said that was positive going into the system. And then we also have minus 50 because the work is going from the system to the surroundings, or applied by the system to the surroundings. So let's go ahead and finish this up. 180 minus 50 is 130. Add 200 to both sides. And then we have 330 joules as our final value for our internal energy. So typically you probably don't need to break out the delta U into a final minus initial, but you may have to if you're looking for a very specific initial or final energy. So in all these cases, I would say a very simple little diagram as I started each problem with is probably going to be helpful. Also just kind of writing down your signs. Once you get to the mathematical part, just some simple algebra there. So as long as you understand the concepts of what's positive and negative, everything should fall into place after that. So I hope that was helpful to you. Thank you very much for watching and listening.